All right, MYP physics. This isn't something that really happens to us in Ghana, but in a cold, dry place like where I come from in Canada, up north, it's an everyday occurrence, okay? And that is static charge or static cling. So if I take a look at this guy's hair, all right, and if you ever wake up and you put on your shirt and you find that there's a sock stuck to the back of your shirt, that's due to static electricity, okay? And that's due to building up a charge on top of an object, all right? Now, the point of today's topic is not calculating charge or calculating the forces between charge. It's understanding the principle of electric fields. How does a charged object feel another charged object in space? How do they interact? Because there's not hands pushing and pulling things. They're interacting through space, okay? And as I talked about, electrostatic forces are non-contact forces. That's what's amazing about these demonstrations. That's what, when you go to any science museum and somebody touches this Van der Graaf generator, usually they'll have a big one. They'll get a kid to stand up, put their hands on it, and then their hair flies out. And everyone's like, ooh, ah, because hair is moving and nobody's touching it. It's usually quite an interesting demonstration, all right? And that's because non-contact forces are magical, like I was talking about in the last videos, all right? Because it appears out of nowhere. But the way they work is that they create a field around them. And sometimes you can feel that in old television screens. If you put your hand close to the screen, you can feel like a fuzz. That's you're feeling the electrostatic field interacting with the particles on your hand or the hairs on your hand, okay? So what we have to try to do in this little video today is figure out how to describe what is an electric field and to draw it. What does the electric field look like around a charged object, such as this metal sphere on top of the Van der Graaf generator that's positively charged? What does it look like? Okay, and his hair gives us a clue. Okay, the hair is mapping what the electric field looks like around a charged object. Okay, so if I was to take a look at these diagrams, let's imagine I took this Van der Graaf generator, okay, and then around it, I put 100 small positively charged pieces of paper around it, okay? As soon as I sprinkle those positively charged pieces of paper around it and I turn the Van der Graaf generator on, what I'll be able to do is see where those pieces of paper fly, okay? And where they fly is going to tell us the direction of the magnetic field, and we call those field lines, okay? So these little pieces of paper would fly in all these different directions, and the direction that a little positive test piece of paper, or positive test charge, would fly around an object maps out the electric field, okay, the direction of the electric field. So what we can see is that the electric field around a positive point charge, okay, so that's like the Van der Graaf generator, the positive point charge on top of it is emanating a field such that if I place a positive test charge anywhere around here, the direction that that charge goes shows me where the field is. Okay, so imagine I sprinkled hundreds of dust particles that are positively charged and we took a video. We would see these radial lines go off. And if I map those radial lines, what I'm seeing is the electric field around the object. Now, something else that's important is that as those field lines separate, as they get more distance between them, the greater the distance between those lines, the weaker the field is. Okay, so the strongest part of the field would be as close as we can get to that positive charge. The further away we get, the weaker the field is. Okay, now what does the field look like around a negative object? Well, it's going to be opposite. If I put those positive dust particles around, instead of flying away, those positive particles are going to fly towards that negative charge. Okay, and it's still going to map. They kind of look the same, just the direction of the arrows have changed because the direction of the field is the direction that a positive test charge would fly. Okay, so positive charge outwards, negative charge inwards, and it's the same thing. You see how close these lines are here? The strength of that field force would be the strongest here versus out here. And it follows something that we learned in Coulomb's law called the inverse square law. Okay, the further away we get, the weaker the force is going to be. All right. So what is the definition of electric field strength? Okay, we know how to draw it. We know how to feel it. We can explain that electric field is what a charged object would put into space. All right, if I took a charged object and threw it in outer space, technically, on the other side of the universe, another charged object would feel it, but it would just be very, very small. So what's the definition of an electric field strength? Well, electric field strength is the force experienced per unit charge of an object at a specific distance from a point charge. So if I'm the unit charge, if I'm a coulomb of charge, and I'm placed at this point, at that distance away from that charged object, it would be the force that I'm experiencing per charge that I have, okay, which is newtons per coulomb, okay? That's the units for an electric field strength, and that's the symbol for an electric field strength, okay? So the electric field strength here would be measured in newtons per coulomb, okay? And if I had 1 coulomb of charge, or if I had 10 coulombs of charge at that specific place, we both would experience the same force per unit charge, the same electric field strength, because the distance between these lines are the same. So at that point, regardless of my charge, I would have the same field. I'm at the same field strength, okay? The force is going to be different, but the field is going to be exactly the same. And if I get closer, my field strength gets stronger, and it doesn't matter what my charge is, I'd have the same field strength, but the force I would experience is different, okay? So how does that work out? How do we get to this equation? Okay, well, remember the force that I'm experiencing is equal to K, Q1, Q2 over R squared. Okay, so let's call this Q1 and let's call that Q2. So if I'm Q2, I'm the point charge Q2. How do I rearrange Coulomb's law equation? I kind of went a little too crazy with that line. How would I rearrange Coulomb's law equation to get my electric field strength? Well, to get electric field strength, all I'd have to do is remove my charge at that point, at R, okay, and I'd have to move it over to the other side. So the electric field strength is going to be that's my electric field strength, which is going to be equal to K Q1 over R squared. So what does that mean? Okay, what does that relationship mean? Okay, it means that the electric field at any point, okay, is going to be dependent on the total charge of that object in the center. That's what it is over here. The greater the charge, the stronger the field strength. And the field strength is going to get way stronger the closer I am. All right, so that's what that relationship means. Okay, that's what that is. Okay, so the electric field strength is defined by the force experienced per unit charge at a specific place in the electric field, and that's the formula. So if I was to give you the charge of an object and ask you to calculate what would the strength of the electric field be 1 meter away, you would have to plug it into this relationship over here. So 8.99 times 10 to the 9 times the charge of that object at the center that's creating the field divided by 1 meter squared. Okay, that's the formula. So how do I draw field lines if there's more than 1 point charge? So it's not, in outer space, we don't just have 1 point charge hanging out. We might have a couple or 3. So let's just draw some simple cases. If I had 2 positive charges that are separated in space, what does the field look like? If I was sitting right over here, what kind of field strength would I be feeling? How much force per unit charge would I be feeling? So what I need to do is I need to put some test charges around here. If I put a test charge here, it's going to fly straight up. If I put a test charge here, it's going to fly in that direction. If I put a test charge there, it's going to fly in that direction. If I put a positive test charge there, okay, you get the idea. And likewise, on the other side, it's doing exactly the same thing. Now notice it's symmetrical, okay? Now, however, if I put a positive test charge over here, it's closer to this positive test charge, so it's going to experience a greater push from that. But as it's pushing and starting to fly in this direction, it's going to start experiencing a repulsion force from that. Remember, it's a positive test charge. So what its path is going to look like is something like that. And the path on the other side is going to look something like that. And the path of a particle on this side is going to look, it's going to look something like that. Okay? So if I was sitting right in the middle, if I was a little positive speck of dust right in the middle, I would be experiencing an equal amount of force pushing me in that direction and an equal amount of force pushing me in that direction, which is kind of interesting. What happens there? What happens there is that I would be stuck. Okay, that would be a point where I would be absolutely trapped in the middle. I have equal push on either side, and essentially at that point, I would experience zero net force, which is pretty neat. So that my electric field strength right there, due to being pushed on both sides, is going to be 0, okay? but all these other points I have values. I'll be moving. So that's what the field would look like in between two positive charged objects. Right in the center, I'd have a dead space, okay? Now I can go and look at what would happen to the field if I had a positive and a negative charge, okay? So if I had a positively charged object and a negatively charged object, what would the field look like, okay? So if I was right in the middle, if I was a little speck of dust right in the middle, I'm going to be attracted and I'm going to be repelled, okay? So I would have a field line that goes straight across. If I was here, I'd be pushed and then I would go there. If I was here, I would be pushed, okay, and vice versa. You make this interesting pattern. All right, and then I'd be coming in here. If I was a positive charge, I'd be flying in over there. And that's what the field lines would look like between a positive and a negative charge. So if I was somewhere in the middle, in the last example, I had no field, but here I'm going to have a real strong push to that side because I'm going to have an attraction plus a repulsion. So the electric field strength is going to be pretty strong, pushing me in that direction. All right, and that's something you'll see in the physics classroom notes, drawing what the electric field would look like, okay? And then using some calculations, you'd be able to calculate the electric field at this point due to that charge, okay? I can do that, K times the charge times the distance between here. Plus, I would have to add the force that's pulling me from here, so it'd be another K Q1 negative charge times the distance, and I would add those together, and that would give me my total electric field, okay? So what can we do with electric field? Why are we so interested in calculating it? Okay, so if I'm in a space, if I'm at a point over here, okay, and the question doesn't give me the value of the charge here or anything. It just says that if I'm at a point P, outside of a charged planet, for example, and my electric field strength at that planet is equal to 1,000 newtons per coulomb, okay, and I am an electron, okay, what I can calculate is the amount of force. What force am I going to experience, okay, for that electron in that electric field? Well, in order to calculate that, the force is going to be equal to my electric field strength times charge, the charge that I have. So the force that I'm going to experience, if I'm an electron, what direction is my force going to be? The electron is negatively charged, the proton's positively charged, so an electron would be attracted. Okay, so what was the force of my attraction? Well, that would be 1,000 newtons per coulomb times, what's the charge of an electron? Negative 1.6 times 10 to the minus 19 coulombs. Okay, so then the force that I would experience is equal to negative 1.6 times 10 to the minus 16 newtons. Okay, so what's this minus business, negative force? Well, that just means it's an attraction. Okay, if it's negative, it's an attractive force. If it's positive, it's a repulsive force. Okay, so now we can see that we can calculate forces in electric field as long as I have a charge, the charge of the object that's going to be moving, and I have the electric field strength, I can calculate the force. Why do we want the force? Well, after calculating the force, I can say calculate the acceleration. Okay, so remember the acceleration is going to be related to F equals ma, that's Newton's second law. So 1.6 times 10 to the minus 16 newtons is equal to 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron. Very small mass. Okay, times the acceleration. So 1.6 times 10 to the minus 16 newtons divided by 9.11 times 10 to the minus 31 kilograms is equal to the acceleration that I'm going to experience, all right? That's going to be a pretty fast acceleration. Look at that, minus 16 divided by minus 31. That's going to be moving probably faster than the speed of light. That's That's crazy. That's a super, super fast speed, okay? So then another question I could ask later on is going all the way back to kinematics. If you know your acceleration and I know my distance, I can calculate, I could say, how long is it going to take for that electron to smash into that positively charged planet, okay? I can do a bunch of questions like that later on. And that's just showing you how we can tie together everything we learned this year all the way from the beginning of the year to now. As long as I can calculate a force, I can do anything that we did in mechanics, all right? So the last thing, and this is important for one of the problems you're going to have in your classcraft challenge, is calculating the field strength between charged plates, okay? Because we have fields all the time that we use on Earth, but it's not like I go outside and stick a Van der Graaf generator in my compound and then everything starts flying. All right, in your computer, in your laptop screen right now is a very, very strong electric field. And your laptop screen is working based on that electric field moving things, okay? And the way it works is that it takes a plate, two metal plates, you can imagine that's your screen on a side view, and it attaches it to a battery. So this is voltage, a battery. Okay, and then the battery, as you know, if you take a look at, we'll look at batteries in another video later on, but a battery has a positive side and a negative side. Okay, so the battery if I plugged that in, I would create positive charge on this plate over here, and I would create negative charge on the plate over here. Okay, and let's say that those plates are separated by 1 centimeter in space. Okay, well, those positive charges and those negative charges would be created on those plates. And if I put a positive test charge, sprinkled the dust in between those plates, they're going to start to move directly across. And so this is what the field lines would look like. Nice and even. They're all moving towards the opposite plate. Okay, and if I was right on the edge, I'd be pushed this way, but then I'd be flying in over here. So that's what my electric field looks like. Okay, that's the electric field pattern between those plates. Now, what I want to calculate is what would the electric field strength be, which is newtons per coulomb. So how much force per unit charge is one of those little positive dust particles experiencing over here in the electric field, okay? And what's interesting is, you see the spacing is all the same? What that means is that a positive test charge is going to experience the same amount of force per unit charge anywhere in between these plates, except for the edges. Anywhere in here, it experiences the same electric field strength. And in physics 11, you'll be able to derive this equation. I'm not going to make you do that, but one way you can calculate it, the electric field strength in between two charged plates is going to be equal to the voltage that you applied, so that the battery, is it a 9-volt battery? Okay, if you plugged a 9-volt battery to plates and divided by the distance between the plates is going to give me my electric field strength. So for example, if this is 9 volts, your standard 9-volt battery, your electric field strength is going to be equal to 9 volts divided by 0.01 meters. Now remember, and I want to get that into your heads, you always have to convert centimeters into meters whenever you're doing anything in physics. And so what is the answer there? Okay, so 9 divided by 0.01 is going to be 900 newtons per coulomb. Okay, that's the electric field strength. Okay, so if I was a proton over here, the force I would experience, okay, so the force of a proton at that point is going to be equal to 900 newtons per coulomb times positive 1.6 times 10 to the minus 19 coulombs. Okay, that's how I would go about calculating the force that I'd be experiencing at that point in an electric field. Okay, and the cool things that we can do with this, and something that was done later on, just to give you a little hint, is I can make stuff levitate. So if I take a plate, okay, all right, and let's just say I took a little droplet of oil. This is an oil drop. And on that oil, I have 0.001 coulombs of charge. Okay? And that charge is negative, okay? It's a negative charge. So what's going to happen? That negative charge is going to be repelled, and it's going to be attracted to the opposite plate, okay? But that oil has mass. So what else is happening? If that oil has mass, it has a force of gravity acting on it, okay? So I could make an oil drop levitate. Oh, I can't spell levitate. I have a feeling it's levitate, okay? I can make it float in air, all right? And if I make it float in air, I can do that by attaching a battery. And if I knew the distance between here and here, all right, what I can do is I can make my electric field such that the force due to my electric field is equal to the force of gravity. Okay, so if I created an electric field such that the force due to the electric field, that force that's pushing up, that's my force due to the electric field, if it becomes equal to the force of gravity, there'll be no net force on that oil drop, and I can make it float. So the force due to the electric field is going to be my electric field strength times the charge of that oil drop, which is equal to the mass of the oil drop times the acceleration of gravity. Okay, that's the force of gravity on that oil drop. Okay, and so my electric field strength, I can calculate what electric field strength would I need in order to make it float. Okay, I can do that by rearranging this equation. If I know the mass of the oil drop, I know the acceleration of gravity, and I know the amount of charge, which I told you, you got charge here, I could be able to calculate the electric field strength. So I would have to tell you the mass of that oil drop. Let's say it's like 0.001 grams or something like that. Okay, I can plug all those variables in, and then I'll be able to calculate. It says, okay, in order to make it float, you need an electric field strength of that. And then I can go backwards from that to figure out, oh, what voltage do I need if I know my distance? And then I can dial that voltage in, and I can make that oil droplet float in an electric field. And I think in your problem, you have to use this electric field elevator to accelerate something up, okay, at a constant acceleration. So I'm not going to tell you how to do that, but I'm going to say that this is probably really important in order for you. This whole setup is probably really important for you to answer that problem. All right, good luck.